Hi, my name is Soteris Demetriou, and today I'm going to be presenting Codrive, a solution for improving automobile positioning via collaborative driving. This is work conducted in collaboration with Puneet Jain, then at Hewlett Packard, now at Google AI, and Kyu-Han Kim, who is leading the Mobility and Networking Lab at Hewlett Packard. First, I'd like you to consider the following scenario with me. Imagine you live in the suburbs of a big city like Chicago, Illinois, and that you have a meeting, let's say at 10 a.m. in downtown. You launch your favorite navigation app on your phone to see how long it will take you to reach your meeting point. The app, given Chicago's traffic, says it would take anything between 30 minutes to an hour. So you leave at 9 a.m. So in worst case, you'll be there at 10 a.m. for your meeting. Now, once you enter downtown, your GPS loses its lock, and now your app tells you that you're on State Street, even though in reality you are on Michigan Avenue. To make things worse, you get stuck in traffic and your lane is not moving anymore. The left lane seems to be moving a little bit faster, so you switch lanes. Of course, as soon as you make that decision, the new lane now comes to a full stop and the old lane starts moving. To make things even worse, you have to make a right turn, which is coming up, but you cannot switch back to the right lane, and you end up being late for your meeting. So why did this happen? Well, navigation apps use dead reckoning using Kalman particle filters to track one's driving route from microelectromechanical sensor or MEMS sensor readings. However, dead reckoning approaches rely on a good initial positioning and also tend to accumulate error over time. Thus, we need a way to correct positioning every now and then to rectify for those accumulated errors. And navigation apps typically leverage GPS readings for that. However, GPS has an accuracy of 5 to 10 meters, and that is in clear line of sight, which accuracy can degrade to 30 meters in deep urban canyons or urban environments where we actually need it the most. Some have proposed leveraging studied landmarks such as BLE beacons to correct vehicles' positioning. However, these approaches typically come with both a deployment and a maintenance cost. However, we observe that next generation sensor-rich vehicles can do better by utilizing their advanced visual and distance sensors. Nonetheless, this doesn't help if you're driving a 2002 Toyota, like the one I was driving at the time. But what if I told you that even if you do drive a 2002 Toyota, every time you drive next to a Tesla or a Google autonomous vehicle, your location could be corrected with close to lane level accuracy. Indeed, we're proposing a solution that achieves just that. Our solution is called Codrive, and this solution is independent of studied landmarks or lane markers, makes no assumptions about phone placement on legacy vehicles, and makes no assumptions on specific hardware requirements. This is how it works on a high level. So on an opportunistic encounter, the sensor-rich vehicle uses onboard computer vision to detect the legacy vehicle, and then it extracts its visual fingerprint and calculates its distance and angle from itself. The sensor-rich vehicle then shares its observations with a compute node at the edge, and also the legacy vehicles through the Codrive smartphone app share their own location as captured from the GPS APIs on their smartphone. The edge node will then compute new plausible positions for all cars that are participating in the same traffic scene, and it's going to communicate those new positions back to the participating vehicles. This way, we can present a more accurate positioning of the vehicle in the navigation app. The first challenge we encounter when solving this problem is that we did not actually have access to a sensor-rich vehicle. Instead of simulating what these cars can see, which might entail unrealistic assumptions about their accuracy, we decided to emulate them. This is the mount design we ended up adapting after a couple of efforts. It can carry secularly mounted phones and a Velodyne LiDAR at their center. We then implemented an infrastructure based on the robotic operating system to synchronize the streams and combine the streams from these heterogeneous sensors that are involved in our mount. Let us demonstrate that through a short video. What will be the end result of this infrastructure. Now imagine we are here at the intersection of El Camino Real and Page Mill Road in Palo Alto, California. And what I'm gonna show us are real world recordings taken by our processing mount and our processing infrastructure. As you can see, our infrastructure captures data from the vehicle's front, near, rear, right, and left view. It can also detect vehicles, and for each detected vehicle, based on the depth sensor, it can calculate how far that detected object is and what is the angle of each of those observations. These are all the assumptions we made about the sensing capabilities of next generation vehicles. We believe this is a conservative approach, since autonomous vehicles can, of course, do much more, right? Okay, I think now we have a good idea of how this can be used in practice, what kind of data is being collected in practice. So now let us see what the sensor, once we get the values from the sensors, how can we use that data to refine the locations, the positioning of all the vehicles that we see in the sensor-rich vehicles surroundings. And to explain that, let's consider the following scenario. Instead of going through the mathematical formulation of the problem, I'll try to explain how we approach this using visual hints. So let us consider the following scenario. So we have a legacy vehicle on the road with two sensor-rich vehicles nearby. That's vehicles 1 and 2. The legacy vehicle thinks it's here based on its smartphone GPS. Moreover, the first sensor-rich vehicle thinks the legacy vehicle is actually here relative to its own positioning, which can also be imperfect. And of course, we might have a third observation made by the second sensor-rich vehicle, which thinks that the legacy vehicle is actually here. So now we have three imperfect observations about vehicle number 3. So let us break down these three observations. So observation number 1 is where car 3 thinks it is. Observation number 2 is where car 2 sees car 3. And observation number 3 is where car 1 sees car 3. Now, the goal of the optimization is to minimize the distance between those disparate reportings. And the optimization is not solved for each vehicle independently, but instead it aims to minimize the collective positioning error, taking into account all vehicles, their location reporting, and interdependencies that belong to the same traffic scene. To capture those dependencies, we construct a set of constraints to guide the solution to the right direction. Firstly, when a GPS receiver reports a location, it does so with specific confidence. Also, when a sensor-rich car reports the positioning of a detected vehicle, this is relative to its own positioning, which is also acquired with a certain confidence. And this confidence is inherited in the reporting of the observed vehicle. Thus, we constrain our solution to be within the intersection of these GPS confidence regions of each of the reportings that we have available for a specific vehicle. Second, each vehicle becomes part of the traffic scene when it's detected by a sensor-rich car. And also, a sensor-rich car can detect the distance and the angle of the detected vehicle from itself. And this is with the help of these high-definition depth sensors. The estimated locations by the optimization for these two vehicles, so our result, our calculations of our optimization problem should respect those constraints. In case a vehicle is detected by two other vehicles at specific angles and distances relative to the detector car's own notion of positioning, then we allow the solution to be somewhere in between those observations. That's the second set of constraints we introduce. That's the angular distance constraints. And lastly, given the GPS constraints and the geometric constraints, the optimization should find a solution which preserves the shape of the traffic scene. Right? However, the whole scene might be misplaced. And to address this, we introduce a new set of road constraints, which restrict the solution to be within the boundaries of a nearby road. So let's see how well this works. We compare Codrive with three other approaches. As a baseline, we use the GPS positioning. When possible, we acquire real GPS readings from smartphones. We also simulate GPS errors to test our design in a variety of other settings as well that might not appear during our real-world experiments. For example, we use the Rayleigh distribution as a good way to approximate the magnitude of those errors. We also compare against a simplified version of map matching. Map matching projects the GPS reading to the nearest road segment, and we use the open source routing machine, OSRM, in our implementation of map matching. And lastly, we implement a version of Codrive which does not use optimization and just is based only on geometric calculations based on the depth sensor. Now, Codrive without optimization, as I said, relies solely on calculating new positions of legacy vehicles based on the distance and angle of an observation by a sensor-rich car. This should be enough, for example, if the positioning error of the sensor-rich car is negligible. Our evaluation aims to assess Codrive's ability in one, preserving the aerial view of a traffic scene, and two, in reducing the positioning error for sensor-rich and legacy cars. To answer the first question, we conducted the following experiment. We consider a topology of 15 vehicles in 3 lanes. This scene consists of 2 sensor-rich vehicles and 13 legacy vehicles. We simulate the GPS error using a 3-meter median for sensor-rich vehicles and a 6-meter median for legacy vehicles. Here you can see the aerial view of one instance of this experiment for each of the approaches, just to help us visualize the result if we were to use any of those approaches. We construct the ground truth, that's the first one on the left, by manually setting place marks on specific GPS coordinates using Google Earth, and we compare with the positioning calculated with the different approaches. Let's first compare the shape of the scene with the GPS approach. Obviously, GPS readings are independent of each other, and the end result will reflect that. So you see how it looks like. Next, let's compare with map matching. As expected, map matching snaps, go back here. as GPS. We'll move forward to map matching. Here we go. Okay. So as expected, map matching snaps all GPS reporting to the center of the road. This might work well if we have a single lane environment, but obviously it doesn't work very well if we have a multi-lane setting. That's the main limitation of that approach. Let's now compare with Codrive without optimization. Obviously, it does much better in preserving the area view of the traffic, but we could still do better in approximating the ground truth. And lastly, let's see how Codrive with optimization, how does it do in this scenario? And clearly, we can see that the last version of Codrive, the optimized version, can reconstruct the original area view of the traffic almost perfectly. Of course, our evaluation did not rely on a simple and single observation of one instance of the experiment, and we in fact repeated those experiments 100 times for each of the approaches and used a popular shape analysis technique to calculate the similarity with the ground truth. The results are analogous with this instance, that is, only Codrive can perfectly reconstruct the area view of the traffic. Next, we wanted to evaluate Codrive's ability in reducing positioning errors. We calculate the error as the distance between the ground truth and the predicted position based on each approach. For each experiment, the data points consist of this error for each of the participating cars, and each experiment is repeated 100 times. I will show the average error for each sensor-rich vehicle and legacy vehicle separately to showcase mutual benefits in this symbiotic relationship. Let's first consider the following experiment: a 3-lane topology with 9 cars, 1 sensor-rich car, and 8 legacy vehicles. The GPS readings for each vehicle were captured using smartphones placed inside the vehicles within the Hewlett-Packard campus in Palo Alto. We perform again this experiment 100 times, and let us now see the average positioning error for the sensor-rich vehicle. We can see that map matching actually increased the error in this case, where the GPS error is low to begin with. And only Codrive reduces the error for the sensor-rich vehicle, achieving in this case a reduction of 28% compared to the baseline. So a great result for us here. Next, we wanted to evaluate Codrive's performance in an urban setting where the positioning problem becomes more apparent for legacy car drivers. Since we could not drive 9 cars in a controlled way in a downtown, we had to simulate this setting. Thus, we used the Rayleigh distribution, which describes the GPS error to simulate it. For legacy vehicles, we set the median of the error to be 30 meters and the standard deviation to be 50 meters. For sensor-rich vehicles, we expect them to have a much better notion of positioning, albeit not perfect, as we use a median of only 3 meters and a sigma of 1 meter. And I will now report the cumulative positioning error for the 8 legacy vehicles in this scenario. Here we can see where the big benefits of Codrive manifest. In a downtown scenario, Codrive can bring a GPS error of 48.9 meters down to 4.3 meters. This corresponds to an astounding 92% reduction. And this is great because it's exactly in these kind of scenarios where we expect opportunistic encounters between legacy and sensor-rich vehicles to happen. Now, those were only a few experiments out of the variety of experiments we conducted. We also assessed Codrive in different topologies, changing the number of lanes, the number of vehicles, conducting the same experiment on different road segments, and also we assessed its performance in reducing errors for various GPS accuracies for both sensor-rich and legacy vehicles. And we found that Codrive consistently outperforms all other approaches. It remains robust to topology and road segment changes and continues to reduce GPS positioning errors as the accuracy of sensor-rich vehicle positioning degrades. So in summary, we have built the sensor card mount and a supporting infrastructure that can be utilized to emulate sensor-rich cars. We've implemented this supporting infrastructure based on the robotic operating system to synchronize and combine streams from both visual and distant sensors. We then design an optimization framework to improve vehicle positioning. And then we perform an extensive evaluation demonstrating great reductions in GPS positioning error for both sensor-rich and legacy vehicles, which is shown to reduce GPS errors up to 30% for sensor-rich cars and up to 92% for legacy cars. And that's all. If you have any questions about our work, I'll be very happy to answer to your questions. So please reach out to me directly for those.